Okay, so then let's start. Good morning to everyone. My name is Andreas Polin, for those who don't know me. I have the honor to chair this morning session. And before we start, I would like to say thanks to our central IT services for recording the session. And also thank you to the Förderverein der Technischen Fakultät, for helping out with the outreach activities. Well, probably you know that my roots are also in software engineering, and for that reason, it's really a pleasure to announce Dr. Christian Macho to you. He's giving his habilitation, or more or less his training presentation or proposal for the habilitation project. It's about building intelligent continuous integration systems, or reducing build overhead with prediction, dependency analysis, and automatic repair. So that's the title. Christian is a postdoctoral researcher at the Software Engineering Research Department here at the Alpen Adria University in Klagenfurt. And without further ado, I would say, yes, welcome to everyone. Thanks for your attendance, and the floor is yours.
Thank you very much. So, yeah, right in time. Thank you. So also from my side, thank you for coming, joining this talk, and good morning to everybody. Andreas already kindly introduced me, so I can skip this slide. One comment for you as listeners to this talk: you see that I'm already working since approximately 2020 on these topics, and I didn't do this talk so far, so don't expect too much from the very beginning. There will also be some results that we already achieved, so this will be a mixture of results and outlook to what we are planning to do in the next couple of months. So as Andrea already introduced a little bit, my research is mainly located or situated around the larger topic of the software automation pipeline. So many of you are doing some research in software engineering even, or applying software engineering tasks in their daily lives, also in research or industry, and you might notice DevOps or continuous integration, continuous delivery cycle, and that's where my research is located. So usually we start with some planning and coding, and then we try to build and test our system. So we are mainly located with this research on the left side. We do not touch too much the operations side with my research. Why is this so important? Because these automation pipelines are a quasi-standard in industry. So this rather outdated number of 40% of open source systems in 2017 already used some kind of automation pipelines in their projects. And as of now, this is already 9 years old. There are quite more projects using this, so I would estimate this is rather doubled in numbers or so. Okay. Why is this so important for industry and for us? Okay. Ideally, we want to have every change that we do to the software project being integrated in the system that is already there, being tested, and also maybe even without further ado can be deployed so that the user has a production system and can leverage these changes immediately. This idea is quite nice. The problem with this idea is the following: if we do this very rigorously, we do a lot of work, and this is very, very expensive. So this all of that costs very much money. So the infrastructure costs money. All this stuff that we runs on some infrastructure, sometimes in cloud systems, sometimes on bare metal. So all of that costs a lot of money. Also the developers, when they are waiting for their feedback, when they produce new code, all that costs money because developers cannot easily switch tasks like we can do for other tasks. For that reason, these change sets are usually kept very small. So they try to have only small feedback cycles and very short feedback cycles, which helps to have easier and frequent integration, less conflicts during integration, so less bugs, and also the easier tracing of bug-inducing commits, which means if you do something wrong, you have only a small span of things that you need to check. As I already said, ideally this is something that you trigger a change or CI execution for everything that you do on the system, and this is quite a lot, as we will see in a minute. Overall, we do a lot of repeated work that is not really necessary because we repeat all the full pipeline for most of the commits we do. If you transfer this to a rather known metaphor, so if you put to a dish that you cook just a little bit more salt, you have to do all the quality assurance for all the dishes that you do. So this basically is very much overhead, as you will see for the lunch, for example. Speaking in more software engineering terms, this is a picture of one project that I picked, and you see that there is a lot of simultaneous things going on, right? So every line is a development thread, and each commit is represented as a dot, and you see that all of these things are more or less in parallel, and each of these dots is one of these items that I said was going through the pipeline. So this is a rather, I would say, medium-sized project. So if you think about larger projects, larger companies, then you can estimate that this is even worse for larger projects. Speaking in numbers, Amazon, for example, estimated a couple of years ago already that they had about 136,000 deployments per day. Does anyone know out of memory how many seconds a day has?
80,000 something.
It's 86,400. So it's about more than one deployment per second for Amazon. Of course, for their whole platform, not only for what we see at Amazon, but that's quite a lot. Same story for Microsoft in about 2017. They had 42,000 deployments a day for all of their stuff. So this is quite a lot that is going on there. And as both numbers are not up to date as of now, that is probably also here much more right now. So overall, this is our main motivation, because what this ends up is that we waste a lot of money for doing things that we already did and did a couple of times in the past. So what my main research goal of this habilitation project is, it's all about improving the efficiency, quality, and reliability of these software automation pipelines by using or minimizing the build breakage, so the errors that these pipelines can produce, and also with some outlook to resource utilization, so that maybe we can have some more efficient usage of these pipelines. So the first question that we can ask here now, where can we save the money? Because there's quite a lot of work going on. Where are the probabilities that we can save money very well? Well, if we go back to our DevOps lifecycle, or the continuous integration lifecycle on the left side, we plan for, or I plan for, 3 main points where we can have some kind of improvement. The first is during the build themselves. So if we can save builds as a whole, if we better know when to build and when not to build, that's one advantage, so we can selectively run the builds and do not use too much power for that. Secondly, of course, when we are programming, so when we are doing our code stuff, when we're programming code or configuring our software, if we have more tool support, we can better avoid breakages, we can better avoid idle times of developers. And finally, of course, the third one, because we cannot capture all the problems beforehand, sometimes the build pipeline will break, sometimes we'll have to debug that stuff. So also after something was built and tested, when something went wrong, we can have means for automation or help the developers so that they can better or more efficiently use the build automation pipelines. This is also the 3 pillars, I would say, from my habilitation proposal, so the 3 research directions that we want to tackle within this project. So the first one, as I said, we try to have prediction models or crystal ball things, more or less, where we want to do, is this CI run really necessary? Do we need to run all the parts of the CI run, or is it sufficient if we run only parts of it? Which are those parts? And of course also explanations why this is the case, because otherwise the developers will not trust us too much. The second, we usually focus on one of the largest issues in software automation pipelines or in programming, in software engineering as a whole, dependencies, because they are usually causing more nasty errors. If you have problems with dependencies, this is usually something that is really hard to debug. And as I said, the last one, if prevention fails, so if we cannot prevent something from breaking, we try to provide means to repair that automatically or with the least effort by the developers. For the rest of the talk, I will go through the 3 pillars and present some parts that we already have done, and also, of course, outlook what we are currently doing and planning to do further on. So for the prediction models, the main goal of these models is to reduce the build overhead. So as I said before, we have a lot of overhead going on, and what we want to achieve is that we want to somehow cleverly or intelligent or smart reduce this workload. One attempt that is in our research community quite established, I would say, is test case selection prioritization. For example, only executing tests that are affected by the changes, or only executing tests that are actually important, whatever important means to the project. The problem is this is one step that we can already reduce quite a lot, but still is a lot of tasks that are executed. You need to compile, you need to download dependencies, you need to deploy and stuff like that. So there is a lot more than testing and the project. A very extreme idea is to ask ourselves, do we really need each of the commits to be integrated via CI? So do we really need to have all of the commits running through all of the pipeline? And the maybe answer that you're also thinking about right now is that probably this is not the case. For some kind of commits, for some special types of commits, we might not have to run everything from scratch again. The problem is we need to select somehow these commits which we want to provide to the CI and also those we don't want to provide. So there is already some prior work, of course, we're not the first ones to do that. Also the platforms like GitHub or GitLab offer this functionality to skip CI runs manually right now by providing some kind of label to the commit message so that the system knows, okay, this is just a commit, we don't need to run all the CI. The problem is, first of all, the developers did not know too much about the functionality. However, this can be easily fixed by training developers and telling them there is this functionality, please use it. The second problem or issue with CI skip is that they don't really know when to skip. So also developers themselves are not sure when they should actually skip and when the CI should run. And this is a much harder problem that you need to tackle because you cannot just tell them some patterns or rules, as we will see in a minute. So there are two main prior approaches to that topic. One that actually told the developers or told the system such rules, skip when only the README changed, skip if there are only comments changed. So these are quite trivial rules to avoid a lot of CI runs already. And a more sophisticated approach which leverages machine learning approaches, incorporating those rules and also data from other occasions like from build history, from experience of developer and so on. Both of them were quite okay. The metrics that they proposed were quite solid. The problem or the main problem that they have is that they actually use the commit message. So and if you look at the commit message, this is actually from the data set of the two works. What the machine learning model is actually learning is if there is something like update readme, skip it, which is basically the rule that they proposed in the first paper. So this is somehow learning what we already know, okay? So this is, of course, a little bit better in terms of metrics, but in terms of practical usage, this is not what the developers actually want. So we set out to improve this a little bit and include some more sophisticated or more clever selections. So for example, if you look at this code before and the code after, what do you think? Should this run through the CI? So the differences are highlighted in red. Basically, what kind of thing do you think is done here? It looks like it's just a refactoring, or actually two refactorings. So the variable was renamed and we removed this separate calculation. So what do you think? Does this change the functionality somehow? Does it pay off to run half an hour of CI for them? Probably not. Maybe it does. Maybe it has some side effects that we don't know from this very brief excerpt that we have here. But at least we can think about not running the CI immediately with them. And that's exactly what we are aiming with our first, or the first part of this habilitation work. We want to incorporate the semantics of changes. So what was actually changed? How was it changed? Not only thinking about how many things were changed, for example, and also the complexity. So was it a very small, very easy change, or was it a more complex, rigorous thing that we actually maybe want to pass through all the tests again? So we set out also to introduce a machine learning model incorporating more targeted, I would say, variables, for example, types of developers, and also on training on historical developer decisions. So the CI skip labels that have already been done by developers, so we can learn from them. This turned out to work even better as the prior models, which is really good. So you see here, depending on which project, of course, this data is always a little project specific because some projects work better, some projects not work better. So we see that we are mostly on par or even for some metrics a little bit better in terms of inter-project prediction, which means that we train and predict projects in isolation without looking at any other projects. Overall, this improved the state of the art a little bit. We didn't do statistical tests so far on that, so we don't know whether this is a significant difference. Could also be a selection thing from the projects that we have. However, we use the same projects as they use, so the comparison is quite okay, I would say. What we have as a huge advantage.
What is A
yes.
O?
So here, A is the approach from Abdel Karim, that's the colleague, and O is our own. Sorry, I didn't tell that. So we are on the right box. For precision, we are a little bit better on median. For recall, we're a little bit worse. For F-score, we're also a little bit worse. And for AOC, we are again better. We did not measure for Matthews correlation coefficient so far, which would be a better metric, because the colleagues didn't measure that, so it would be hard to compare anyway. Speaking of transfer learning, so we also did cross-project prediction, so training on one project and predicting the others, which was our assumption that we are better because we don't rely too much on project-specific models. So we see that this assumption or this hypothesis was kind of confirmed, because here you can see we are mostly better, except for recall, than the prior approach. Again, we have the red boxes is the prior machine learning approach by our colleagues, and O is our own one. And in terms of AOC, we improve it quite a lot. So apparently our model is better in generalizing things that you can transfer from one project to the other. We also looked a little bit not only on the metrics themselves, but also we checked what are the important attributes that our model uses to actually decide whether a CI should be skipped or not, which is then also interesting for developers to understand this decision. And it turned out that the history is quite interesting, which is kind of questionable, because you know if there are 5 already skipped, skip the next one, could be treated as somehow okay, clear, or maybe a completely wrong decision. But there are also other things like time to the last, since the last commit, which could be a situation where somebody's just trying something out, committing all the time, and you don't only want to actually run the last commit through the whole pipeline and not all of them. What's interesting, also code change types, so what you actually changed. Did you change an if condition, for example, or did you change the parameter list in a method, is quite important in this model. So this is the first part from this first pillar, let's say. This is kind of done, I would say. We have to plan for a conference to submit it, so it's not accepted yet, but it's for ongoing work. And we plan it for SANA 2007, which is approximately in autumn of this year. So now you can ask, well, this is quite okay. I would say this is even a good thing that developers can use, but is this something that changes or helps us out with all these CI automation problems? Well, to some extent, yes. The problem is we lose one important thing, that is the information of the build run. So when we skip a build run for whatever reason, we don't get any information about this. So would it have been successful? Would it have been not successful? And all of that we lose, and especially trends. So if you see that your build results are degrading, so over time you get more and more failures, you lose all this information because you do not run the CI. This has the impact that the risk assessment for your CI pipeline and also for the managers becomes much harder, because you cannot really say, okay, there's still a healthy CI pipeline or not. So we set out to also preserve this information, at least partly with prediction models, and this turned out to be something, same model, but what we now predict is not only we should skip or not, but the actual outcome of the build. Okay, so instead of should we run or should we not run the build, so what would be the expected outcome of this? And also here, some preliminary results, I would say, because we have not an accepted paper, it's just submitted. We are quite okay with that. So if you look at the metrics again here, so this is now no comparison with other works, because there are barely other works that provide enough material so that you can reproduce their work, unfortunately. With our metrics, we are quite good. So the boxes are very small, so our model seems to be very stable, independently on which projects. And they're also quite high. So we have AOC values around 97, I would say. And also the Matthews correlation coefficient, which is really important for imbalanced data set, which we have here because we have a lot of unbalanced data in this area, is quite okay with ranging over 86. What I have to say here, this is not a project-wise comparison, but for all projects at all. So this is kind of we call it holistic setting, where we try to leverage all the information of all the projects. For one simple reason, we want to have a model or something that everybody can use, and not that you have to train yourself on your project, and maybe this is not transferable then. Also here, we looked at the variables, so the data that we used, what is actually interesting, and we see that again, the historical stuff is very interesting, but what is also noteworthy here, the experience of the developers, so how they are experienced in terms of CI and also in their programming, is quite important for that. When we looked in the data, it seems that developers that are long in the project, developers that are more experienced with CI and pull requests and all that stuff, are more likely to have successful builds, which is kind of a thing that you can also act as a company, because you can train your developers for doing that. In this work, we also did one thing that is, I would say, very different to other works, because other works usually do some kind of stratified sampling and randomization of the data, which basically can lead to the fact that you use future data to predict the past, which is kind of not really that what an application of this work would allow. So what we did here, we did the sorting of the data, and we only used actual data that has already been there for predicting the next commit, so to say. So we used, for example, here, the first 4 commits to predict this build result of the 5th one, and so on. This is much more practical, because now you have actually at what the developers in practice can do, because they cannot use simply the data set and predict something with the future data. Visualizing this leads to the plots that we see here. So we have on the x-axis time in terms of commits, and on the y-axis the respective metrics. On the left we see on the left we see the metrics over time, and we see that after some ramp-up phase where the model is still kind of struggling around and not really performing, after some time this model stabilizes for all the projects and is quite performing, even in terms of Matthew's correlation coefficient. I hope you can see it on the slides here. There is also the a priori ratio of successful builds in green and failing builds in red, so that you have some kind of comparison to what this model actually achieves. So it's quite well predicting successful and non-successful builds. On the right side, you see the development of the important attributes over time, and also here, in the very beginning of this model training, so the first couple of commits, the importance of the attributes is quite changing. So for the first models that are quite bad, of course, different attributes are important than for the others and later on. What is interesting, that over time, in most of the projects, I have to say, this also stabilizes. So you have then 1, 2, 3, maybe sometimes 5 attributes that are actually really important and remain important over time, which told us, well, this is quite a good finding, because that's something also the companies can work with. Worst case would have been that they struggle around and the model is still working quite well, because we have a good model to decide, but the interpretation is quite hard. So I already mentioned this before in the other work. Also here we have the integration of so-called historical metrics. So we leverage the recent results of the build outcome, of the last couple of outcomes, to predict the next one, which is quite hard. Okay? What we tried here, we removed these attributes and only relied on things that are not historically relevant, like commits, source code changes, build code changes, developer experiments, and things like this. And it turned out, of course, that the model is a little bit worse than with this information, but according to the numbers, it's still quite good compared to the other approach. And if you compare it to approaches of other colleagues, we still outperform them quite well. So especially for AUC, we quite outperform them really much. Okay. So what to get with that? The explainability of the model increases. So other attributes become more important than how were the last 5 commits actually building, because this is only from statistical relevantness. So this work is actually currently submitted, and we are awaiting an answer from the editor every moment, actually, because it's quite a while being submitted to the Journal of Systems and Software, and we hope that it, of course, gets accepted soon. So now coming back to our main topic of this talk, build overhead reduction. So how do these actually help reducing our build load? Well, first, the limitation, we haven't assessed it directly, so we don't know whether this actually helps developers and actually helps them to focus on their work more. But what we can say is both works indicate, and with their ability to predict those commits, that the overhead might be less for the developers. As I said, we still have to figure out what is actually the case, but we are quite sure that this will turn out to be true. So what are we planning on that pillar? Well, combining these approaches, so we can also use the prediction of the build result to decide whether the build should be run to the pipeline or not, because this would quite be interesting. If we are quite sure that this build will pass, we might not need all the detailed information. If we are quite sure that the build will fail, we might want this information, so we can then better decide which build to run or not. So speaking from my 3 research directions, we now finished the first one with this prediction, with the crystal ball. Both approaches are quite helping developers. Okay. So now we can move on to the second one, to the dependency optimization, which is then during the coding of the project, let's say. First of all, we all know that code is reused quite often. So all of you that actually work in somehow software engineering or that build some projects, most probably didn't build it from scratch completely, because there is some work already been done. There are frameworks, there is code that you have in your company. So you reuse the code. This is quite normal, state of the art, I would say. What you get with this for free is dependencies in your project. So if you're project A and you're using other projects from your company or even third-party libraries, you get something like this. So you depend on other things, and the problem is also these projects might depend on other things. So this increases the complexity of your whole project quite a lot, because you can easily use other software and easily get a very huge dependency graph then. What problems arise from that? Well, all these versions are not always compatible with each other. So there might be some projects that do not work with other projects quite well, and this gives you additional complexity. So all the combinations that you might not want to have, you need to figure out. There is no plan that says you cannot use this version with this version for all the projects. Also in terms of security, sometimes you don't know what are the third, fourth, second level dependencies that the projects use. They might be vulnerable, so might be vulnerable in your project as well. So the first thing we did on that research direction, we formulated a couple of such problems, dependency smells as we call them, and investigated the project, how frequent they actually appear. So is this actually a problem that developers have, or is this just something that we think they have as a problem? One of the smells that we defined is the so-called jump call, where you have dependencies in your dependency tree. You have a project A depending on project C, and this depends on the API guardian API. However, we use the API guardian API directly with a call or a variable usage, for example. The problem is, if we remove project C from our dependency list, we will lose all this information and the project will not work anymore. So this is actually, as we will see later, quite frequently happening. And the more severe things, I would say, because you don't see them immediately, dependency conflicts. So you have dependencies to the same project, but in different versions. So the 3 projects A, B, and C all have dependency to project D, but in different versions. And this is especially for projects like development environments like Java, really problematic, because you can only decide for one that you will have in your project, and all the others might not work. So fixing these problems can be really hard. Like detecting might be comparably easy, but fixing those problems might be really hard because also of the huge search space. So when we talk about these dependencies, the repository holding all these dependencies in the Java universe right now holds about 90 million packages, and the problem is this is not getting any better. It's vice versa, it's getting even worse. So this is the statistics of the last 10 years, and you see the new packages per year is increasing quite a lot. So this is actually from yesterday, the statistics. So we are now middle of the year, and if we just double this, we will again exceed a number of dependencies this year. So selecting the 1 or 2 correct ones out of this possibly end of the year 20 million libraries is quite hard. So our goal at this research direction is how can we help developers to manage their dependencies, to find the correct ones, to eliminate the problematic ones. First thing that we did here is detecting those problems and reliably detecting those problems, the dependency smells that I mentioned before, how frequent do they actually occur, which of them are actually occurring, and how often they actually occur per project and type. So in that sense, we use a Klingo solver. So we formulated all the project in rules and facts for Klingo, because then we can derive the problematic smells for our project. What we have to consider here, all the versions that exist, all the transitiveness that exist, and also, of course, the conflict potential, which means we then have to formulate all the smells that we have in Klingo rules to derive the smells. What is the cool thing with that? First, we have a checking mechanism, so we can identify with Klingo pretty easy which smells are occurring, how often they are occurring. And as Klingo offers also the possibility to give you solution candidates for that, this is quite handy for us, because we only have to ask, give us possible solutions that do not violate any of the constraints, for example, do not have any jump calls, avoid conflicts, and so on. In more technical detail, so you don't need to understand all the stuff that's now on this slide, what we formulate are all the dependencies. So for example, project A has a dependency on project B, project B has a dependency on project D. So project A has a transitive dependency on project D, for example. And also all the calls that are done in the project. So if a method main calls something from object B, method foo, all of that is encoded in Klingo and used for detecting the smells that we've formulated. In the end, what we will get is a jump call as a result, because we know that we are using from project A something that is in object D, which we do not have a direct dependency to. So this is actually pretty straightforward rule. Assessing a couple of projects with that, we found that these smells are actually pretty frequent. Especially what we found is if some smells are happening, they are happening quite frequently. So if you look at this column, these are the jump calls. In this project, we have 366 up to almost 1,400 jump calls in one single project. So there are method invocations that actually skip one dependency, or maybe more of the direct dependencies. Similar for the different types of smells. Detection time. So we can ask how long does this take to detect, actually, because this is also very crucial for developers, that they don't have to wait too long. Actually pretty fast. So the longest one that we estimated here is about 50 seconds, 54 seconds. This is something, a time that the developer can easily wait, because the tests might even run longer than this. So this is also very interesting from a practical point of view. So to conclude that, these problems that we formulated here, these smells are happening quite frequently. So they are in most of the projects, and if they occur, they happen quite often. The problem with that is that the so-called hidden problems are very prevalent. So jump calls or shadow dependencies, that you have dependencies in different versions on your class, but this happens quite often. And I'm pretty sure that developers are not too aware of that, because nobody is actually really checking the whole dependency tree. However, these things are really hard to detect manually, because you have to go through all the calls, all the code of the dependencies, and check where this actually happens. And this is something nobody does, because it's simply too much effort to do. Also, this work has already been accepted at the Journal of Systems and Software, so this is already out. Speaking from this detection, we are quite good with that. However, what we want is the remediation, so coming from a bad situation to a good situation back again. So this means we need to find a solution, as I said before, because of constraints of ripple effects and the huge number of packages in the Maven universe. The automated finding is really, really helpful, because developers will have hard times to select the correct dependencies. What we find here, when we measure the dependencies before and after the repair approach that we applied with Klingo, we see that all the smells decreased. So the black bar is before and the right bar is before, and the 4 smells on the right decrease all after the repair. What in contrary increases are the declared dependencies, because of course we have to have more direct dependencies if you want to resolve some problems with that. Although this is quite in a number of more dependencies that are quite acceptable, so it's like 10% more around all projects. Speaking of the jump calls that we earlier looked at a little more detail, almost all of them could be eliminated. Why is that the case? Well, this is a quite easy fix once you detect it, because you simply declare the dependency that you have as a direct dependency. And our approach does exactly that and does it quite well. On the opposite, what is much harder to detect and also much harder to fix, as I call it here, the holy grail of dependency problems are dependency conflicts. So like the figure points out quite quickly, very illustrative. We have two dependencies of the same type, but with different versions. And if we have both of them on our project, that will cause a problem. Unfortunately, most of the time when we run the code, so you cannot easily detect it statically. Also here, our approach could remediate most of them. So if you look at that column where we have the actual conflicts on the left side, so one project with even 128 occurrences of dependency conflicts, which is quite a lot, and we could reduce this number to 42. Why not to 0? Because it's simply not possible for this project without changing the code itself. So only by modifying dependencies and the dependency structures that they have in their code, we could reduce already quite a lot. Also this work, so this is more or less an addition to the accepted work, is planned for autumn, possibly for the SENA conference, because it would fit the topic quite well to being published. So to conclude this part of my habilitation work, all of the approaches that we now saw notably optimize the dependencies in one or the other way. One approach does highlight all the problems, and the other even helps you to reduce all the dependency smells automatically and even dependency conflicts. What is really good for that, this is not a machine learning model that you just get a decision. You get an informed decision because you can trace back why this decision has actually been taken and why the dependency has been excluded or included. So you can trace that back pretty nice. Back again to the main topic, overhead reduction. How does this contribute to the build overhead reduction? Well, not directly, of course, because there is no build involved in what we saw so far, but it's an indirect reduction because we help the developers that they don't have to run the pipeline so often to find out what's wrong and to don't run the pipeline to find out what is the details of the problem actually. This is actually an underestimated problem because people often just run the systems and run the stuff on the servers as long as they don't cost too much because it's much easier. What is still open here? Well, we have some limitations we need to adapt from developers, of course, and of course also the machines are not always correct. So also our approach here has some limitations in terms of correctness. For most of the reasons of that are code-related reasons. When you have inheritance, large inheritance, reflection, and this is also hard to cover in the effects that we need to provide to Klingo. What we are doing on top of that right now, two topics basically. Once using the same idea to reduce the vulnerabilities in the dependencies, so with adding vulnerability information to our solvers, we'll also get informed decisions which dependencies to avoid and include concerning vulnerabilities. And for developers, very interestingly, to generate tests when we are planning or doing dependency upgrades. So when you change your dependency list, what we want to do here is to give you some kind of generated tests that you can verify that you didn't ruin anything of your programming code while updating the dependency. Unfortunately, this is still something that developers do not really do because the argumentation is we will find out that with our tests that we already have, and they are usually not sufficient to do so. So this brings us to the last pillar, to the last research direction of my planned work, which is when everything failed, the prevention could not catch the stuff that we are basically doing. We need to have some means of repairing all what happened before. So far we have some kind of cost reduction. This is quite okay, but the problem is also in fixing those things when they break, because then you have some kind of pressure to do so, because the build should be run all the time. Otherwise it's interrupted and everybody else cannot really proceed. So what we had with the first two approaches, we can detect the stuff when we don't need to run it. We need to have some predictions for build outcome prediction. The problem is, if this fails, we also need something to help. Or in speaking the metaphor, if the alarm doesn't work because the battery is low or some other circumstances happen, we need to have the fire extinguisher to remove the fire, otherwise we just will burn again. And similarly, this holds for our software pipelines. If we don't have corrective repair, we only have this preventive maintenance. We are kind of still in the pressure to repair everything because this is something that we need to do. So our approaches for automated repair are manifold, so I'm only presenting today one particular thing that is, I think, the most recent or most up-to-date one. Earlier approaches used like manual approaches, so error analysis and complexity with dependencies manually analyzed, which is very error prone, which is very hard to do because many logs are really large. There are also some automated approaches like we did during my PhD, for example. We could fix some specific problems much faster than developers, and we could automate a couple of things that are already done when builds break. The problem is these strategies are very limited to specific scenarios, tailored to specific scenarios, and we always have to run the build oracle. So we have to run the build afterwards, which means that we don't really reduce the load right now. I would even say that this approach increases the load. Why is this so hard? Well, some of the problems are not explicitly stated. They are under the hood. You need to really take care of what the dependency problems are, and you really have to have a lot of knowledge about the project itself and also the ecosystem. And as I mentioned before, the solution space is quite huge. So again, these 20 million dependencies, finding the correct 10 that possibly fix your bill is quite hard. And as we found out during this study with the repair, the log files, which should basically help us to narrow down the errors, narrow down everything that we did, are very verbose, are very complex, and you need to figure out what's actually wrong. So this, as a consequence, consumes a lot of time from the developers, and they are actually blocked from really doing their stuff, what they want to do. So coming back to the log files, this is some very, very small excerpt of a report of a build execution from the Maven clean package command. Do you immediately see what's the problem with this error? And I can tell you that the log files are usually magnitudes of size larger. So I'm going to help out a little bit. The actual interesting stuff are those two things, to know which module failed and that there is a dependency that is missing. So if you're an experienced developer, you might look at this first because you might anticipate what's the problem, but still you need to find even that snippet in the whole bunch of log file. So there are a couple of approaches addressing this. Our approach to doing that we did recently is to leverage LLMs for that, because they are like language models, as the name suggests, quite good in summarizing, quite good in extracting information from plain text, which log files are. And our approach actually could, to 95% accuracy, extract the actual build outcome, so whether the build failed or what was the reason that the build, what was the reason that the build failed, or if the build was successful. So only in 4.5 of the cases it was not clear. Basically, these were very, very infrequently happening problems that the LLM just did not grasp as a problem. It also outperforms all the static state-of-the-art approaches, like the Maven log analyzer that we built a couple of years ago, mostly in the extraction of the build error details. So the static approaches leverage regular expressions to extract, and you can assume that these regular expressions also evolve over time. So there is a point in time when the static approaches are simply outdated and you need to adapt them. What is the advantage of our approach? You don't need to adapt it because the prompt remains the same, and the LLM hopefully adapts for that and can then still extract the error message and the error details. So our experiments showed that we tried with a couple of large language models that the GPT models are on the DevStral small model are quite good in their predictive performance. You can see the F-score on the y-axis, and compared to its runtime, because this is also very important. So less runtime is better and better performance is better, of course. So all the models over here are the best in terms of our study. There are also other LLMs such as the Quen model, which is quite good, but it takes a lot more time to extract everything. So this is then impractical for the developers because they have to wait a lot more. this work, so evaluating the large language models, whether or not they can extract our information from the bin analyzers, is also currently submitted to the Journal of Systems and Software. And also here we hope that very soon we get some feedback on that. So from this log analysis, we have solved one of the future problems, namely that the log is really hard to read, so we can extract all the information concisely that we need, but still the repair is not done. So we have this prior approach called BuildMedic that we did in earlier time, which could repair about 60% of the missing classes and 54% of the dependency-related issues, so dependencies are with the wrong version and so on. This is quite good, but also here we have these repair strategies which are static and cannot evolve over time. So also here we want to have something better, and there is some room for improvement. And as the time, of course, makes it very, very nice to do, also here we use some kind of large language model approach, kind of agent-based, if you want to call it like that, for the missing dependencies. So we gave the LLM the error message, and we asked to find something that is repairing the build. Basically asking the LLM to provide us with some actions, adding, updating, or removing the dependencies, or giving more information about the universe. And it turned out that this is actually working a little bit better than the static approaches. So you see in total, for both of the experiments that we did, one with the full log, so we gave the LLM everything that the log outputted, and on the second part, the parsed log, where we gave already a reduced error log, only where the error details are provided. So for some, it did not work quite well depending on the used model. Also here we did a comparison of 3 large language model, and the Qwen3 coder was most of the time the worst one. GPT-OSS, the smaller version, was quite okay. Most of the cases, the larger GPT model was the best one performing on this task. If you look overall, depending on which variant you choose, the best performance that we have is with the large GPT model, which could repair up to 83% of the studied cases for missing dependencies. Also here, the time is an issue. You could say, okay, we can also look up the mail from Central and look which dependencies are there, but this is happening in a matter of minutes rather than a matter of hours. So out of this work, we have one paper that is already accepted at the SENA conference and was already presented as well. And we plan an extension for that for our main conference, the ICSI, which is this next Wednesday. So we plan for that to submit the extension of it there. So if you recall the dependency conflicts, and this is now the last part for this talk, these are quite hard to find because we don't know by static means. We have to execute something usually. So what we set out here is tackling the main problem of it, not only fixing it with dependencies, because as I said, some are not fixable without modifying the code, because this is simply not possible. And things like this, or errors like this, that the API changed, are usually only being able to fix with changing the code. So for example, here you have a session save method that saves the data of the user, and the compiler says it couldn't find it anymore. And if you look in the documentation, you will see that this method was simply removed and you should use a different version. So this is something an LM can easily understand, also a developer could easily understand, but we don't read too much the documentation. So in that sense, we try to automate also this, and LLM here was a game changer because we could really easily generate code that is compilable, that is actually doing what we want or very close to doing what we want. And what you see here is a very preliminary evaluation. So we could fix with 0 repetitions most of the cases. The green bar tells you that the build and the tests were successful, and the red bar only that the build was successful, but the tests are still broken, so semantically it changed something. What is really nice on this, we see that most of the stuff could be repaired with only 1 iteration, and only a few needed more iterations to repair again, which is quite good also in terms of time, because then you can also argue that the developers will fix the things faster. So to sum that up, this is very promising. There is still a lot of work to do here because we need to incorporate this in other settings as well. But the first results are promising. So to sum up, what we did today, or what the habilitation work is actually about, reducing the build overhead. And all of the three pillars that I presented so far are contributing to that. So all of them basically reduce the overhead and so indirectly reduce the cost that we have for having some runs running on the cloud or even on your bare metal machines. And the view of the system, CI system still remains. So the problem is this is still reactive rather than proactive and the rule-based rather than intelligence-driven, as we could call it. So the vision that we have also on after the habilitation talk is that we cannot see, or we should not see the CI as a monolithic thing that is telling you something after you did something, but more as an automated system that helps you to build better software. You know, this is the trend like everywhere, bodies that help you, automated things that help you with tasks, that you don't have to do so much things. So I want to transition to a collaborative, very specialized, of course, and smart environment that helps you building the software without losing quality, but maybe even doing that faster. So some ideas that we shared, having something like this, that you get more explanations in these CI tools, that you have more information about what went wrong and even suggestions, so that you have more or less a communication and more or less a collaborative effort with machines to help you better automate the software pipeline and produce better software with better quality. So this concludes my talk, and if we have still time, I'm open for questions.
So, yes, well, first of all, thanks for the presentation. Very interesting, very inspiring.